Alright, welcome back everybody. In this video we're going to look at solving related rates problems. We're going to start with one example and we'll see how far we get here. If you read through the note sheet, you see there's kind of a basic outline of the process that you want to use to solve a related rates problem. So we're going to follow through with that process as we go through these problems. Let's start here with example 1. A tanker is spilling oil into the water, resulting in an oil slick that is close to circular. Since it's close to circular, we're going to treat it like it is circular. At the time that the slick's diameter is growing at the rate of 8 feet per second, the diameter is 250 feet. At what rate is the area of the oil slick increasing? So the first thing I'm going to do is draw a picture and name the variables and constants that we have in this situation. Alright, so we'll make our circular oil slick. Let's try that again. We'll make our circular oil slick, and it's a very brightly colored oil slick. But it's circular in nature, and the one characteristic that we do know about this oil slick is we know its diameter. And we're also talking about the area. There's actually nothing that's constant in this particular problem, so there are no constants for me to introduce. Now, as far as the variables that I have, I already named the variable. I use a capital D for diameter, and that's a deliberate choice. I don't want to use a lowercase d because once I start taking derivatives, it gets very, I use that lowercase d a lot. Alright. Write down the numerical information that we have in terms of the symbols that we've chosen. Alright, the slick's diameter is growing at a rate of 8 feet per second. That is the change in diameter with respect to time. That's 8 feet per second. The diameter at that time is 250 feet. So those are the two pieces of information that were given in the problem. I wrote those down so that I know them. Write down what we're asked to find. At what rate is the area of the oil slick increasing? So we're looking for the change in area with respect to time of this oil slick. That's our unknown. The next thing we want to do is we want to write an equation relating these two variables, diameter and area, because we're given all of this information about the diameter and the change in diameter, and we want to find the change in area. So we want an equation that relates area and diameter. And we'll start, we know the formula for the area of a circle, I hope. The area is pi r squared. We also know the relationship that area or radius is equal to 1/2 of the diameter. And so by substituting that into this area formula, I can get a formula for the area of a circle based off of its diameter. And we get that the area is going to be pi over 4 times the diameter squared. So there's our equation. Now we want to take the derivative of this with respect to time. Both area and diameter are changing as time changes, so it makes reasonable sense that we can find their derivatives with respect to time. And we'll go ahead and do that. The derivative of area is going to be dA dt. And the derivative of the right-hand side here is going to be pi over 4 times the derivative of d squared, which is going to be 2d dd dt. Alright, and now in order to find dA dt, all I need to do is substitute the values of the two variables that I know. I know that dd dt is 8, so I'm going to put 8 in here for dd dt. And I know that d at the moment in question is 250, so I'm going to put that in here for d. And then I can calculate the value of dA dt. It's pi over 4 times 2 times 250 times 8. And if I multiply all that stuff out, let's see, I've got, if I cancel 4 and 4, got 2 times 250 times 2, we end up with 1,000 pi. Now I need units. At what rate is the area changing? And there's a couple of different ways to do this. We can kind of reason our way through it. It represents the change in area with respect to time. Area of this oil slick is going to be measured in square feet, since the diameter and the change in diameter are measured using feet. And time is going to be measured in seconds, since the change in diameter is measured in feet per second. So the change in area with respect to time is going to be square feet per second. Another way that I could kind of reason my way through my unit if I got stuck here was noting that the unit for this measurement, well, first off, noting that the units for these two measurements there are no units because they're constants in the equation. But the units for this measurement is feet, and the units for this measurement was feet per second. And since I'm multiplying those two things together, I multiply feet times feet per second, and that gives me square feet per second. Alright, that's the end of example 1. We'll come back in the next video and look at example 2 from this lesson. See you guys next time.